Welcome to second half of chapter 4. It's conformational analysis. Challenging, somewhat challenging concept. Let's start with 4.8, physical properties. Section 4.8 is physical properties of alkanes. We're not really going to talk about this very much. You should read this section, review section 3.4. Really what we want to get into is section 4.9, and that is conformational analysis. We're going to analyze different ways in which these molecules arrange in space. So 4.9 starts us off with ethane. We're going to take the simplest molecule, aside from methane, the simplest molecule with a carbon-carbon bond. Methane doesn't have one. So ethane can rotate about the carbon-carbon bond. That's the most important beginning concept that you just need to see, is that rotation around a carbon-carbon bond around or about, sometimes people say rotation about the CC bond, the CC sigma bond, we call this sigma bonds, gives 3D arrangements. They're always changing. It's like the axis of a car. It's spinning. These are called conformations. These arrangements are called conformations. If we look at a carbon-carbon bond, something like this. Each carbon is tetrahedral. We've talked about this a lot. This bond can rotate. Okay? It's rotating rapidly. Now, rotation, like an axis, is different than tumbling in space. Molecules do tumble in space. They're always kind of floating around, rolling around, adjusting, but they also rotate, and that's really what we're focused on. So for ethane, there are two conformations. There is the eclipsed and the staggered. Let's start with the eclipsed. I will bring models to class so we can spend some time looking at these. What we mean by eclipsed is if you're looking down this bond, okay, sometimes we'll see a little eyeball in the book. I don't know if she does that. I've seen that in textbooks before, but imagine you're looking down this carbon-carbon bond here, okay? So you're looking down there. What you're going to see is going to be eclipsed with this H. You're going to see this one, A, let's call it, in front of B. And when you look down there, you see something. You see down the carbon-carbon bond. We call this a Newman projection. This is just a different way to view these molecules, a very important way. The carbon is implied there. And what do you see? You see an H back here behind. And the way we draw that is all three of those H's are behind. So let's circle the two that we mentioned that are eclipsed. They're all eclipsed. All three pairs of hydrogens are eclipsed. This angle here we talk about is a dihedral angle, it's called. And again, we'll bring some models in. You should build these models with your plastic model kit. We'll talk about what we mean here. But the angle between that H, from H to carbon that is behind there, back up to H, that angle is 0. The angle that you're looking at is 0. The H's are directly in front of one another. Now we can rotate 60 degrees along this dihedral angle, i.e. the axis is going to rotate. And what do we see now? We're just going to rotate the front only. This H right here, we're going to put it 60 degrees. And now we have a staggered orientation. And the same thing, now we're going to draw the staggered conformation here. We'll rotate this 60 degrees. All we're doing is looking at two different perspectives of the same thing. So when we rotated that, it's on the right over here. So that means it's now wedged and up. It's up and to the right, so to speak. The back carbon hasn't moved. Nothing has changed there, so let's keep our two circled. But now the circled one in the front is coming out towards you. Okay, these are equivalent. These are equivalent to each other. So if you look at these Newman projections, N-E-W-M-A-N, these Newman projections, which has a lower energy, and it's the staggered. Lower energy is really important. Energy is the staggered because there is no longer an interaction here. No interaction. Whereas here, these are, we're going to talk about what these strains are. So we're always focused on a single carbon-carbon bond. Very important. Okay? So that's ethane. I want you to work on butane. So you can look at that figure 4.7 is, I'm sorry, propane, forgive me. I want you to work on propane. It's going to add one carbon. Okay? You're always considering one carbon-carbon bond. Figure 4.7, take a look at that. That's some homework for you to do. Okay. We're going to now we're going to rotate this all the way around. We showed one rotation. Now I'm going to give you a table with all of these rotated. I'm going to just circle the hydrogen in the front. Here we have energy increasing, going up this scale. And here we have dihedral angle, 0 to 360 degrees. So let's draw. The first one is here, like we drew before. Again, you can look at this. This whole thing is laid out for you in figure 4.8. I'm essentially drawing figure 4.8 for you. Dihedral angle of 0. Happen. Oops, sorry. H is back there. Scratch that. H is back. H is back. So what happens? We're going to click over these, and it's a lower energy conformation. Now the H is going to be eclipsed here, so we're going to rotate. We're always rotating the front carbon. I'm going to have to squish these together a little bit. You can see we're just clicking 60 degrees each time. Circle that H. Okay, it's implied that these are directly behind each other. You want to draw these very carefully, by the way, when you draw them. Now we're going to click another 60 degrees. Here we go down here. The H is now at the bottom. You get the idea. We're going, they're all eclipsed and staggered. There's only two types of conformations, but we're going round and round. So you could finish this off. It's going to eclipse there, and that'll be up here. So put that one in, and then there'll be another one, another stagger down here, and then you're back to 300, 200 or 300 degrees, and that was 240 degrees. This is 180 degrees. You're just going around. You got to practice these, and then when you get to 360, it's the same as 0. Ethane is where we start because it's very important. But it's really just the starting point. Butane is much, much more important. The strain here an eclipsed pair of hydrogens, right, is called torsional strain. You can think of it with the word torque. Torsional strain. The word torque implies that they want to torque out of the plane. Okay, it'll help when we see the models that I'll bring in. I'll talk about this in person as well. But you need to see that this is torsional strain. It's a torque out of the plane. There's some interaction. It's electron pair repulsion. these electron pairs and these bonds here are repulsing one another. They're pushing against each other. So it's less stable. Because there's 3 sets, it's each torsional strain is about a kcal. So it comes out to be 2.9 kcals per mole. So each is about a kcal per mole. Just kind of tuck that away, and let's move on to butane. So butane is 4.10. And now it really gets much more interesting. Butane conformation. Let's go ahead and draw out our Lewis structure drawing of butane. We have carbons 1, 2, 3, and 4. All these sigma bonds can rotate, but the C2, C3 is very special. It teaches us a lot. Okay, so we introduced torsional strain with ethane. There is torsional strain in butane, but now we want to introduce steric strain. So if torsional strain is the repulsion between electron pairs, steric strain is the repulsion between groups, atoms or groups. So increased energy from atoms forced together in space. That's steric strain. Now, what's going to happen is we're going to have 2 different eclipsed and 2 different staggered. Okay, so the eclipsed, just to introduce you to the terms, we'll draw all these. They'll be partially and totally. And with staggered, we have some special words. Gauche, G-A-U-C-H, anti. It's totally staggered and partially staggered, if you want to think about the gauche is partially and anti is totally staggered. These are the common names for those, okay? So the lowest energy conformation is the straight chain form of any alkane. Any alkane, the lowest energy is the straight chain form, where these methyl groups, CH3s, are staggered. They're far apart. This is the anti-conformation. Whereas the highest in energy is this tightly eclipsed. So let's draw all these before we, rather than draw the skeletals, let's draw the Newmans. We'll draw the table. I'm going to borrow from figure 4.9. You can look at this. These are the conformations of butane. I'm going to draw this. I'll draw this a little slower because I want to explain some things. But look at figure 4.9, and I'll draw half of this at a time, okay? And so we have the totally eclipsed. We have the same thing with energy, and we have dihedral angle. So 0 degrees, CH3 is up top. And what do we have? We have this. You can draw it this way too, and break the bond and put the CH3 behind. The CH3s are completely in front of each other. So are the H's. We mentioned it was a kcal for each H, so let's put that here. 1.0 kcals, 1.0 kcals, 2.6 kcals, total of 4.6. It's all relative. 6 kcals. We're going to see, we're going to get to 0 when we get the methyls completely completely apart from each other. So 4.6. This is an absolute maximum, an energy max. Here is a local minimum. And here, this is where the gauche comes in. What do? We rotated 60 degrees. So now the methyl groups are not eclipsing, but there's still an interaction there. This is called a gauche, and we went 60 degrees. So it's still steric strain because they're bigger than hydrogens, but it's about 0.9. It's about a kcal. It's the same a CH3 eclipse, staggered interaction like this, a gauche, is a hydrogen-hydrogen eclipsing. Go another 60 degrees, and it's not going to be quite as high as previously. Notice the CH3 in the back is staying the whole time. Each of these interactions is about 1.4. Okay, the CH3 and the H eclipsing, this is partially eclipsed because the CH3s in front of each other, the totally eclipsed, more energy, it's higher. Okay, there's enough energy at room temperature for this to go round and round and round. That's no problem because it's not that much energy relatively, but we're going to see how these gauche interactions really matter a lot. So that's 120. Now let's go to 180. Again, this is another, that was a local max, local minimum, local max. Now we have an absolute minimum, energy min. And here, I'm going to draw it up here. CH3 in the back has not moved. Oops, sorry, scratch that. I drew the back first this time. And now the CH3 is here in the front, and you got the H and H. So just scratch that little part there. There's nothing there. The CH3s are as far apart as possible. This is the anti. Notice this is the straight chain form. If you draw that out, if you make a model of butane and look down the carbon-2, carbon-3 bond, you'll see this. Now this is 180 degrees, and you can finish this by drawing the 240 and the 300 and back to 360. Make these models, draw them all out. Okay. All right, I would like you to memorize that a gauche interaction is 0.9 kcals per mole. It's about a kcal. It's 0.9. Okay. So you can draw the rest of those conformations. Okay. Really important concept. Go through the book, read, make models, keep working on these. It doesn't, the first time you see it doesn't make sense. Okay, so this is figure 4.9 and figure 4.10 technically. Okay. They do it a little differently the way they lay it out, but it's the same idea. So the one thing I want you to memorize is the gauche or the gauche, 0.9 kcals, really important. All right, so that's acyclic alkanes. Next, I want to turn to cyclic alkanes, 4.11. So we introduced two types of strain, torsional strain and steric strain. Torsional was electron-electron repulsion. Steric strain is atom or group repulsion. Now we want to introduce angle strain. This is an increase in energy when we deviate from a tetrahedral bond angle. Right? We said the bond angle is 109.5. When things start to deviate from that, then energy comes into the system. This is doesn't mean rings won't form. It just means they have strain. So this is cyclopropane, and that angle is 60 degrees. That's a lot of deviation. Butane is 90. Cyclobutane. Pentane, or cyclopentane rather, I think it's about 108. So it's pretty close, but it still has a little bit of ring strain. Same thing with cycloheptane, cyclooctane. They all have angle strain. Except for cyclopropane, all of these rings, they do something it's called puckering. They conform. They conform to reach bond angles as close to 109.5 as possible. So there's different conformations. We're not going to worry about any of those except for the one I left out, cyclohexane. This is a truly beautiful molecule, if I'm allowed to say that about molecules. Cyclohexane, we'll bring a model for this as well. If planar, we would guess that there'd be a 120-degree angle there, all the way around, right? If planar, cyclohexane would have angle strain and torsional strain and steric strain. but as it were, cyclohexane has no angle strain, no torsional strain, and minimal steric strain. Okay? This puckering, this very special puckering that's called a chair, is going to minimize the strain, and that's important. That adopts a very special, again, dare I say, a beautiful puckered conformation that we refer to as a chair. They have a nice little diagram, kind of an Adirondack chair on page 153 to help you visualize it. This is not a regular chair. Use your imagination, but it's we call it a chair. It's not planar. Okay, and so let's work on that. Let's draw this chair. Drawing chairs is challenging. I suggest people draw out the chairs 100 times. It's a good round number. It's essentially 3 sets of parallel lines. So let's draw one out. Okay, doesn't have to be perfect, but I'll tell you it has to be good. Okay, it's got to be close. And we're going to walk through this. What we have here is H and H. Okay, there's H's all around, right? And this is puckering. It's adopting this conformation. And what it has done is eliminated angle strain. It has minimized steric strain and eliminated torsional strain, or at least, yeah, it's eliminated torsional. So all the angles are 109.5. Again, build this molecule. There's no other way to see it other than to build it. All angles are 109.5. All hydrogens are staggered. It's the staggered conformation all around. And what we learned about butane, we're going to be able to apply here. So what we do with butane, we kind of look down this bond, right? We're going to look down that bond, and what do we see? We see in this, now here, we have the ring. I'm going to call it a ring over here, top left. There's an H, and there's an H. That's the front carbon. What's in back? We draw the circle to imply this. There's an H that's up. That was that one up there. There's an H over here. And then what do we have? We have another ring over here, the rest of the ring. That should look familiar. Imagine 2 CH3s over here. Instead of rings, if you imagine 2 CH3s, that is a gauche conformation of butane. Okay? This is a gauche interaction. I want you to draw that connection. Staggered. It's all staggered. It's going to go through eclipsing interactions. We'll talk about that in a minute to get to the other chair, because there are 2 chairs. You need to redraw these over and over and over and over. So now let's redraw this nice and big. I'm going to put in all the hydrogens. Number the carbons. How you draw this is really important. In Chapter 5, we're going to talk about wedges and dashes, but you never use wedges and dashes for a chair. We have 2 types of hydrogens here. This is called an axial, and there are 6 of them. Called an equatorial, and there are 6 of these. Okay? Axial and equatorial do not mean up or down. They mean axial and equatorial. Axial comes from the word axis. This is also axial. Axial can be up or down. Okay, so this is axial up. This is axial down in this representation, but they're on the axis. The axis is up and down, whereas the equator, think of the Earth, the equator going around it, right? If you had the idea being you have an axis cutting through this, up and down. There's your axis. Here's your equator going around. So these are going around the equator of the cyclohexane. So make this and get an idea, right, what we're talking about here. So there can be axial up, equatorial up, axial I'm sorry, equatorial down, okay? So let's talk about ring flipping. That's one ring. I want you to draw both of these 100 times. Ring flip is not a tumble. Okay? Again, this is all in the text. You can use ring flipping 4.12b. It's not a tumble. It is a conformation. Just like butane, when we said that it's rotating about this axis, it wasn't a tumble. Okay, so let's draw the chairs without the hydrogens, and this is in equilibrium. It's not resonance. And what we're saying is, I'm going to draw little circles here so you can kind of see. What we're saying is this is gonna undergo a conformational ring flip. This is chair A. Conformation A. This is the same molecule. And we're going to call this one B for boat. This is called a boat. Looks a little bit like a boat when you make it. Here's our little circles. And so this carbon is kind of pushing up, and that's forcing these carbons here to adjust to this new reality. Okay, this bond is in the back. This bond here is in the front. Okay, and so I'm going to do another flip, and now this one's going to come down, another conformational adjustment, and this is the other chair. Okay, we call this C, chair A, chair C, and B for boat. Again, the first time you see this, it's confusing. This with all the hydrogens in there. When you have the hydrogens in there, you're going to have what are called flagpole interactions. And what you really need to do is track your hydrogens through here. Build a model, track it all the way through, and understand what's happening. And what happens is when you go, for example, axial, this H becomes H equatorial. All the hydrogens are flipped. So this equatorial over here became axial over here. This axial over here became equatorial. Okay, so there's torsional strain in the boat. There's eclipsing hydrogen-hydrogen bonds. And so we've got to go through this many times to be able to kind of follow along. So now we can, once you kind of master cyclohexane itself, then you can look at substituted cyclohexanes. We're not going to look at anything other than 6-membered rings. But there's a rule, 4.13 here. The rule is that the equatorial position is less hindered, less sterically hindered. So it's lower in energy. So I want you to remember that groups prefer to be equatorial. So let's take a look at mono-substituted. We're going to look at this molecule. This is called methyl cyclohexane. So we're going to look at both conformations. Once we start putting groups around, it's a little easier to see what we mean by ring flips. This CH3 is in the equatorial position. Everything is in principle in equilibrium, okay? However, it drastically favors the equatorial. But let's draw the flip. CH3 is down. Okay, you can't change. There's no bond breaking here. So now the CH3 is axial. This bond has not broken. Okay, now it's axial and it's down. Here's our circles we can number the carbons. We'll number some things later. This is conformation A and this is conformation B. We used B for boat before, but it doesn't matter. A and B, we're going back and forth. But this is preferred 95 to 5%. Only 5% at any given time axial. That's how much of a stability factor is going on here. You should always draw the hydrogen on the carbon when you put a substituent. Okay, we'll say this in class and stuff, but the CH3 is in the equatorial. Very important point. The CH3 is down, still down, the way we've drawn it. We could draw it up, okay, but it doesn't change. It's still down. This will become really important with dye substituteds. Okay, there's other ways you can draw it. In fact, your take-home assignment is to move this methyl group around. Draw all 6. Practice drawing these rings with the methyl group at every position. So draw it here. CH3 is down. That's axial. Draw the other one. Draw the equatorial. So work on all 6 of the other 5. The other 5 pairs. It's a good way to practice. So why is this equatorial more stable than the axial? It's a very important question. And so let's draw it again, and we're going to look down these bonds. Let's just draw it with the CH3 in the axial. Okay. I'm going to put in all these hydrogens. Again, you should practice drawing these the right way. Notice that the equatorial bonds are parallel. It's all sets of parallel lines. So we're going to look down bond A, call this A, and we're going to look down bond B. We're always looking down a carbon-carbon bond. So let's focus on A. What do we see? We see a carbon here. We see a hydrogen down. We see a hydrogen up. So let's draw that. And we see a ring over here. So let's draw that in front. This is A, bond, looking down bond A, ring. And what's in the back? This is the second carbon. The CH3 is up here, and the ring, the other part of the ring is over there. It's all the same ring. That's the idea. You always have this gauche. Get rid of it. It's a gauche. But now you've got a new gauche, right? This CH3 is interacting unfavorably with this ring. That's what we're talking about here. Okay. So that's looking down bond A. There's a new gauche. So what's that cost? 0.9 kcals. Now let's look down bond B. When we look down bond B, what do we see? Now the CH3 is out in front. The ring is over on the right. It's a little harder to see this one. H is like this. You get the same. Any bond you look down, you're always seeing the ring. That's the consistent gauche. So relatively speaking, though, there's another gauche interaction. Okay. So it's a total of 1.8 kcals per mole, which equates to 95%. That's why there's only 5% of this one is because of these interactions. It's all being pushed to the equatorial CH3. So it's 1.8 kcals more stable than the axial. What we call these are 1,3 diaxial interactions. There's 2 of them, 1,3 diaxial interactions. Sometimes what we're saying is there's a carbon right here with hydrogens. There's a steric interaction there. So it's a 1,3 diaxial interaction. It's really just a gauche, just like in butane. Okay. So let's look at an interesting trend. I'm going to draw 4 different cyclohexanes. I'm going to draw out the CH3. You're not familiar yet with wedges and dashes. Well, yeah, you are. I'm sorry. We're not getting to stereochemistry, so never mind that. So what we're saying is there's an interaction across this ring, 1,3 diaxial interactions, right? There's 2 of them, 1.8 kcals. That's methyl cyclohexane. That's what we just said. So the axial methyl, there's about 5% of this one, 95% of the equatorial. The same is true for an ethyl. That's an ethyl group. Same idea, 1,3 diaxial interactions. And there's about 4% of this one. Not much difference. Same is true for an isopropyl. Same idea. You have 1,3 diaxial interactions. You can draw it that way. Put the H kind of up high like that. There's about 4% of this one, 96% with the isopropyl and the equatorial. However, there is virtually none of the tert-butyl. Now, what has happened, in all these cases, the H is the thing that's sort of inside that pocket. Now you got a big CH3. It's a much bigger interaction. It's much closer. There is really 0% of this. It's all equatorial, okay? So it's all going to go to the equatorial. You should draw that. The 1,3 diaxial interactions for the tert-butyl gauche are very, very, very high in steric strain. So this will become really important when we talk about dye substitutes. The take-home message is this group never axial. These other groups, if there's a tert-butyl on the molecule as well. Okay? So if you have a methyl, ethyl, or isopropyl on one side and a tert-butyl on the other, the tert-butyl will always win that push. Okay? We'll see when we look at some examples. Okay? I want you to remember that about the tert-butyl. So dye-substituted cyclohexanes, this is an introduction to stereochemistry, and we will get to that in Chapter 5. But you can have 1, 2, so let's just draw a cyclohexane. We talked about methyl cyclohexane. You can put another methyl group at the 2 position. If this is the 1, you can put one of the 2, 3, or 4. Let's start with the 4, actually. 1,4 dimethyl cyclohexane. However, you can have 2 different types of 1,4, and 1,2, and 1,3. And now we see if the CH3 is, the CH3s are on the opposite face. We have a name for that. The CH3s are on the opposite face. Build this molecule. This is called the trans. So you have trans 1,4 dimethyl cyclohexane, and you also have cis. Now they're on the same cis, CIS. Cis equals same. Cis 1,4 dimethyl cyclohexane, if we were naming those. So now let's look at the conformations of both of these. Trans, we're going to go through 1,4 trans and cis, 1,3 trans and cis, and 1,2 trans and cis. Notice what I'm doing. I am sort of translating the trans. Okay, and I'll talk about this in class, but I'm taking this and I'm rotating it. I'm tumbling it 90 degrees in space. So we're looking at, in a planar way here, this group as I kind of flip the ring up and look at it in the 3-dimensional chair-like way. This CH3 is down over here. This one is up, up, down. We could have easily flipped it the opposite direction. I will talk about this in class to help drive home this point. We have equilibrium here. Okay, this is by far favored over the diaxial. The diaxial now has 2 sets of 1,3 diaxial interactions. You should look at those. Think about those. Okay. So, and that would be about 3.6 kcals less stable than the diequatorial. So this would be diequatorial. All right. Now what I want you to do is take home the cis, practice drawing these. The cis are equal in energy. I want you to come up with why. Why are they equal in energy? If this one is greatly favored over the diaxial, then with the cis, they're equal. So I want you to work on those, okay? Let's look at the 1,3. Let's look at a methyl and an ethyl, just to change it up a little bit. That's the trans 1,3. And here's the cis. One, 3. Let's look at the cis this time. Again, I'm just translating from skeletal to chair. So now we've got some different positions. This one is the diequatorial, and it is much preferred to the diaxial. So again, about 3.6 kcals. Notice down, 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 down. Okay. Again, take home, I want you to draw the trans. Draw out the trans, and I want you to see why they are equal in energy. Let's do the 1,2 di-substituted. Go back to the dimethyls, trans, and the dimethyl cis, the 1,2 now. Again, translating skeletal. Should be able to translate skeletal to chair and vice versa. This is drastically more favorable than the diaxial. Now we have 2 axial groups less favored. Take home the cis, draw out both, convince yourself as to why they're both equal in energy. So that's conformational analysis of acyclic, i.e. butane, and cyclic, i.e. cyclohexane derivatives. Okay, so that was 4.13 was substituted cycloalkanes, and then 4.14 is oxidation of alkanes. Right, if you remember, Leo says GER. Oxidation is, we talk about oxidation and reduction in terms of electrons in GenChem, but in organic, we make it actually a little simpler. Oxidation is really a gain of typically CO bonds, but not always, or a loss of CH bonds. Reduction is loss of CO bonds, or maybe CZ. We'll see what we mean by like a CZ bond, but loss of carbon-oxygen bonds and gain of CH bonds. You can also look at carbon-carbon bonds and add hydrogen to them and reduce them, okay? So essentially, we have an alkane, and we have oxidation states. Oxidize, that's the symbol for generic oxidation. This gives you an alcohol. Okay, the names don't matter right now. We're adding a carbon-oxygen bond, so you can oxidize. And now what happens is you oxidize and you go to a carbon-oxygen double bond, for example. That's an aldehyde. A ketone is the same oxidation state. We can oxidize further up to carboxylic acid. There's 3 oxygen bonds. Okay, you can go farther to like CO2 or carbonic acid. But these are the big 3 we're going to be talking about a lot throughout the course, just so you know what oxidation means. The opposite direction is reduction, reducing the number of carbon-oxygen bonds. And then finally, combustion, reaction we're going to tell you that you can do with alkanes. Until chapter 15, you can do radical chemistry, but that's a long way off. But one of the most common ones is you can take an alkane and you can burn them. You have some oxygen. You have a spark or initiator. And you can burn them, and what do? You get CO2, right? People worry about CO2 in the environment from burning alkanes, i.e. gasoline, high octane rating, things like that. You get water, and you get heat, which is energy. It drives you around. And so natural gas, gasoline, jet fuel, etc. It's all the same thing. So what I want you to know is basically that any alkane, so CH4 is the simplest, alkane plus oxygen will give you CO2, water, and heat. Okay, you don't need to worry about stoichiometry. You don't need to balance the equation. But I want you to understand that alkanes plus oxygen plus a spark will give you CO2, water, and heat. And that is where we'll stop. Chapter 4 is done. 5 is next. And we will pick up with chapter 5